Let's take a look at square roots, simplifying square roots or radicals. We're going to review the Pythagorean theorem again, and then we'll look at kind of what it means to be a Pythagorean triple. So here are the list of the first 15 perfect squares, right? 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared, and you can generate this list really easy. You're just squaring the integers. My point is, these are the first 15 perfect squares, meaning the square root of these numbers is an integer, right? The square root of 100 is 10. The square root of 196 is 14. If you try to take the square root of any other number between 0 and 225, you're not going to get an integer, right? The square root of 10 is some decimal. The square root of 9 is 3. So these perfect squares you really have to memorize. They're easy to generate, but there's a list for you. So first idea is, let's see if we can estimate square roots, right? The square root of 20, right? It's just a number. It just happens to be an irrational number, meaning it can't be expressed as a fraction. It's just a repeat. It's a decimal that goes on forever with no pattern, but it is a number. It is a real number. It's just not a fraction. It's not a rational number, as they call it. So let's estimate. And you're like, well, 20 is between 16 and 25. So the square root of 16 is 4, and the square root of 25 is 5. So the square root of 20, I don't know. Let's say it's around 4.5. You could use your calculator, but if you want to get an idea of it as a number, it's around 4.5. The square root of 95. Well, it's pretty close to the square root of 100, so a little less. So maybe, I don't even know, and again, I do not have my calculator with me. Let's guess 9.8, and you could check. It's probably pretty close. But you should be able to estimate square roots values based on knowing the perfect squares around them. Okay, let's work on simplifying a square root. Okay, so we want to reduce the square root of 50. It's not in its most simple form, and you want to think about factoring it. But there are lots of ways to factor 50. You could do 5 times 10. You could do 2 times 25. And what I really want to point out is that there's no reason to factor 50 into something other than its perfect squares. So let's say up here we went the wrong way. You said, well, the square root of 50, I know that's the square root of 5 times the square root of 10. And an algebra property says I can do this then. But that doesn't do us any good. There's no reason to factor 50 into 5 and 10 because the square root of 5 is still an irrational number that can't be reduced, and the square root of 10 isn't. So this idea is true, it's just not helpful. What if instead I took the square root of 50 and I broke it down into 25 and 2? I looked for the biggest perfect square factor of 50, or I'm looking for these guys. Only these guys make any sense because these are our perfect squares. So what I want to do is I want to take 50 and make it 25 times 2. I do know the square root of 25. The square root of 25 is 5, and then the square root of 2 just has to chill out. And so what I'm doing here is I'm taking 50, and I'm saying this, and then I'm saying this. I know the square root of 25 is 5, right? The square root of 25 is 5, so 5 came outside of the square root, and the 2, well, it's not a perfect square, so it has to chill out. Same thing on 27. I'm going to factor it into 9 and 3. The square root of 9 is 3, and then the inside 3 has to chill. So I'm going to rewrite the square root of 27 as 3 radical 3, or 3 square root of 3. Again, 48. I could do 2 and 24, but they're not perfect squares. I could do 4 and 6. I could do 4 and 12, but is 4 the biggest perfect square that goes into 48? And the answer is no. 16 is actually the biggest perfect square factor of 48. So it's 16 times 3. The square root of 16 is 4, and the square root of 3 has to chill. Again, this is how you simplify square roots. And if you pick out the biggest perfect square, this is always really just a two-step process. Factor the number, and then evaluate the big square root. Okay, why are we doing this, right? Why is this important in this particular unit? Well, we already showed that if we're interested in finding the distance between 2 points on a line, it's really just the Pythagorean theorem because you get a right triangle. So let's say I have the coordinate 2 comma -5, this guy, and the coordinate point 6, 1, and I wanted to know this distance. Well, we've shown in class that that distance is the hypotenuse of a right triangle, right? We know the x and the y coordinate system, vertical and horizontal, form a right angle. And if this is at 2 and this is at 6x value, I can label that as, hey, look, I took 4 steps this way, -5 up to 1, I took 6 steps. So we know that the Pythagorean theorem says that 4 squared plus 6 squared equals c squared, where c is the distance between the 2 points. So this is 16, 36, that's 52, and then c is going to be the square root of 52. And what I'm telling you is that you're not allowed to leave it as the square root of 52. You have to simplify it. So you got to take the biggest perfect square, which would just be 4, and you get 4 and 13, and then the square root of 4 is 2. So you get 2 radical 13. This is the only acceptable answer. Now, if you were actually trying to physically do this, and like in your yard or something, the square root of 52, we'll look over here, it's just bigger than 49. So the square root of 52 is probably something like 7.2 or something. And again, you can check that on the calculator. Right, how about this one? Something like this. We get a right triangle. This is at -4 left, all the way to 5 right. That's 9 steps to the right. And this is at 3, and this is at -1, so this is 4. Again, the distance here is going to be 4 squared plus 9 squared equals that distance squared, c squared. And we're just using the Pythagorean theorem. The Pythagorean theorem is a true statement as long as we have a right triangle, and we always have a right triangle on a coordinate plane. So this is 16, 81, c squared. C squared is 97. C equals the square root of 97, and in this case, 97 is a prime number, right? Nothing goes into 97. I mean, nothing goes into it, let alone having a perfect square. So that's as simple as it can get, and if you wanted to approximate it, well, it's a little bit lower than the square root of 100, so it's probably like 9.8 or something. Okay? So, got to know the perfect squares, should be able to estimate their values. Remember, they're just numbers. Should be able to simplify them. We need to be able to simplify them because we are going to use square roots. We're going to get square roots when we do the Pythagorean theorem, when we find the distance between 2 points. And then the last thing I guess I wanted to mention is what it means to be a Pythagorean triple. I might use that word in class. A Pythagorean triple is just one of the really nice triangles because it works out nice. Okay, the most famous Pythagorean triple is just our 3, 4, 5. We know that if we have a triangle that is 3 by 4, this is 5, right? 3 squared plus 4 squared equals 5 squared. 9 plus 16 equals 25. Check, right? The 3, 4, 5 triangle does in fact form a right triangle, and that's actually using the converse of the Pythagorean theorem, which is way later in our unit, but I just want to remind you that you know these. But the 3, 4, 5 is just one of many Pythagorean triples. So you can talk about similar triangles. And again, I know we're going to talk about this in depth later on in the year, but it's nice to talk about it right now as well. That if we have the 3, 4, 5, then what if I double all the sides? What if I make that twice as big and that twice as big? Won't I actually just make that twice as big? And the answer is yes. So if that's 6 and that's 8, then that's 10. You're like, oh my goodness, look, they're like cousins, right? This is like the older cousin of the 3, 4, 5. Or maybe even an older brother. This is the 6, 8, 10. Because if this is true, well then this is true, because they're really the same triangle, just a blown up version, which is what similar is. And you can show it. 6 squared plus 8 squared does equal 10 squared. 36 plus 64 does equal 100, and you can put a check mark there. That's another one. But if this is true, then we can get all sorts of things. We can make this all 5 times bigger. We can look at the 15, 20, 25 triangle. We can make these 7 times bigger. The 21, 28, 35 triangle. That's a right triangle. We all know these Pythagorean triples. We can make it 300 by 400 by 500, right? We can do anything we want with this. We could say that it's 0.3, 0.4, and 0.5. Any of those. We could say 3/7, 4/7, and 5/7. We can make them all smaller or bigger, and we can get as many Pythagorean triples. Now, these aren't really triples because they're no longer integers, but I know they're right triangles, okay? So there are a whole bunch of them. The most popular one is the 3, 4, 5, and all its relatives, and then the 5, 12, 13. Because if you have 5, 12, 13, then you have like 10, 24, 26, and all sorts of things. But these are going to pop up the most in math. And again, the 3, 4, 5 is by far the most dominant one, because the 3, 4, 5, the 6, 8, 10, the 9, 12, 15, the 15, 20, 25 are all versions of this guy. Okay, hopefully this helps you get started on square roots, Pythagorean theorems, simplifying, and then why really we need to be able to simplify.